Welcome to this explainer. Today, we're taking the breathtaking construction of the Akashi Kaikyo Bridge and translating it into a masterclass case study on overcoming literally some of the most extreme natural challenges on Earth. If you're managing complex projects, engineering massive structures, or, just fascinated by how things get built in absolutely impossible conditions, we've got some fantastic, high-level professional insights for you. We're going to dive right into how a single project team managed massive scale, deep water, typhoons, and, get this, a literal earthquake right in the middle of construction, yet still successfully delivered the project.
Connecting Kobe on Honshu all the way to Awaji Island, the Pearl Bridge steps across the Akashi Street with a staggering 1,991-meter main span. That is massive. It's a critical piece of infrastructure deliberately designed to minimize obstruction in a remarkably busy and honestly highly dangerous waterway. Achieving that specific structural purpose required an engineering scale that was just unprecedented at the time.
Here's the roadmap for this explainer. First, we'll meet the Pearl Bridge. Then we'll look at engineering against nature, followed by designing for earthquakes. After that, we'll examine the ultimate 1995 stress test and wrap it all up with core lessons in risk management.
All right, let's jump straight into Section 1, Meet the Pearl Bridge. Spanning a total length of nearly 4 kilometers, the bridge deck isn't just some simple beam. It actually relies on a highly dynamic, 3-span, 2-hinged, stiffened truss suspension system. So for it to function correctly, it has to work harmoniously across a wildly complex network of cables, towering support structures, massive anchors, and specialized movement joints. Imagine being on that project team. You have to continuously balance severe deep-water logistics with high-volume marine traffic, intense seasonal typhoons, and super strict earthquake demands, all at the exact same time. Succeeding here absolutely required fabrication accuracy down to the millimeter, not to mention a comprehensive long-term maintenance plan established on day one.
Okay, moving right along to Section 2, Engineering against nature. To really appreciate the solutions, we have to look at the baseline constraints. The first major hurdle, the sheer depth of the street, dropping down to approximately 110 meters. To put that in perspective, that's roughly the height of a 30-story building completely underwater. You obviously can't just drop massive concrete foundations in water that deep and hope for the best, right? To proceed safely, the team had to use specialized, large-scale, undisturbed seabed sampling to confidently design those foundations. By securing highly accurate subsurface info, they actually proved the supporting ground was significantly stronger than previously believed. This was a total game-changer, allowing for a much more optimized tower foundation and effectively eliminating massive over-design risks. And if deep water wasn't enough, the project also faced rapid tidal currents right near those deep foundations, clocking in at around 9 knots, or 4.5 meters per second. This severe hydrodynamic constraint literally forced the team to develop specialized 3-dimensional current measurement methods just to operate safely. They were out there deploying acoustic velocity gauges and using satellite-based ship position measurements to map the chaotic water flow. This is a really powerful professional reminder for us. Complex field data collection is never just a check-the-box requirement for the initial design phase. It's an active, vital, and ongoing tool for daily construction planning and risk mitigation.
Then there's the wind. A final baseline constraint meant treating 67-meter-per-second typhoon winds as a primary design driver, definitely not just some secondary environmental afterthought. When you're building a main span of this extraordinary length, wind effects and aerodynamic instability are severely magnified. We're talking about the threat of catastrophic structural failure here. So to conquer this, the project team didn't just rely on advanced math models. No, they required a massive physical wind tunnel test facility to verify the exact performance of the suspension bridge design under simulated extremes. They effectively turned physical mock-ups and rigorous testing protocols into active project controls.
That brings us to Section 3, Designing for earthquakes. You see, a long-span suspension bridge survives massive seismic ground motion completely differently than a short, stiff bridge. Instead of building a rigid structure that stubbornly forces all of that sudden, massive earthquake energy into singular load paths, which, let's face it, ultimately results in catastrophic brittle failure, engineers went the opposite route. They designed a long-span flexible system. By embracing flexibility, this design safely controls and dissipates seismic energy. It effectively distributes extreme movement across a really robust network of cables, towers, bearings, and highly specialized expansion joints. It's built to roll with the punches. But here's the catch. To achieve this vital flexibility without sacrificing the usability of the bridge, the team utilized a stiffened truss girder. Now you might be wondering, How exactly does a bridge engineered to move so drastically remain safe for commercial vehicles and daily commuters? Well, the truss deck itself acts as the great balancer. It's specifically designed to distribute those massive seismic forces and resist violent twisting from the wind. In doing so, it maintains the perfectly stable, smooth deck surface required to safely carry heavy highway traffic at high speeds. Pretty brilliant, right?
All this careful planning was put to the ultimate test in Section 4, the 1995 stress test. On January 17, 1995, the Great Hanshin earthquake violently hit the Kobe and Awaji region. And at that exact moment, the bridge was heavily under construction right there in the street. The enormous support towers were already completed, and the massive main cables were actively being built. This earthquake was so incredibly severe and so close to the site that the geological ground physically shifted, literally. This meant the carefully calculated span lengths between those massive towers had actually changed in reality. Talk about an unprecedented challenge for a project team. Yet, despite this massive tectonic shift, the incomplete bridge didn't collapse, it survived. And it survived because it perfectly embodied a core seismic philosophy. Actively avoid the trap of brittleness by engineering the structure to move and flex with the earth. When they did comprehensive post-earthquake surveys, they found that the massive, deeply embedded foundations actually moved in unison with the bearing ground. Because they didn't awkwardly resist or slide against the shifting earth, the structural integrity of the foundations remained fully intact. They completely dodged a catastrophic failure mid-construction. Now, how the project management team responded to this radically altered span geometry is an absolute masterclass in crisis management. Rather than panicking, halting the project indefinitely, or just throwing out the original design, they utilized a highly disciplined verification framework. We can categorize it as measure, analyze, decide, and document, or MADD. First, they precisely measured the newly changed span lengths. Second, they thoroughly analyzed the structural effect of the foundation movement, judging the overall influence to be minimal thanks to the design's inherent reserve capacity. Third, and this is crucial, because some of the central girder lengths hadn't been fabricated yet, they made the smart decision to adjust the fabrication specs for those remaining pieces. Finally, they carefully documented the engineering changes and seamlessly continued safe construction. Just incredible problem solving. Let's extract the big takeaways in our final section, Lessons in Risk Management. If we map the initial environmental challenges directly to the management solutions, we get a really clear, actionable flow for basically any major project. Deep, rapid water currents prove that complex field data collection is a mandatory, continuous part of planning. Severe foundation uncertainty showed us that securing accurate subsurface info directly reduces costly overdesign risks. The extreme wind challenges taught us that physical mock-ups and rigorous tests have to become essential project controls. And perhaps most impressively, the unprecedented span length changes following the earthquake prove that flexible procurement and adaptable fabrication sequencing act as incredibly powerful real-time resilience tools. By engineering those massive substructures to move safely with the bearing ground, the team demonstrated a highly crucial project management takeaway. A major unexpected disaster during a project lifecycle does not automatically equal project failure. It just doesn't. If your core design is built upon predictable structural behavior and significant reserve capacity, an external catastrophe really just initiates a period of disciplined verification rather than forcing a complete operational shutdown. Furthermore, long-term asset durability has to be meticulously integrated from the very beginning of the design phase. You can't just tack it on at the end. To protect the bridge's vital main suspension cables from the highly corrosive salt-heavy sea air over decades, the engineering team utilized a dry air injection system. This elaborate setup actively controls the internal humidity of the cables, which drastically reduces the risk of hidden corrosion. This underscores a massive project management rule. Lifecycle closeout and long-term maintenance planning must start well before the asset is ever open to the public. We've seen how the Akashi Kaikyo Bridge became a total triumph, not by fighting a harsh, volatile environment with rigid stubbornness, but by deeply engineering for adaptability and reserve capacity. So, I want to leave you with this final provocative thought for your own professional endeavors. Since this colossal structure survived deep water, typhoons, and a massive unexpected earthquake specifically because it was built to flex rather than resist rigidly, how can you build that exact same adaptable resilience into your next major project? Something to think about. Thank you so much for joining us for this explainer, and we will see you next time.